In this video, we're going to work a couple of example problems where we find the limit of a sequence where the sequence is given to us with a recursive formula. So in this section, in the opening section of the infinite sequences in series chapter, we're looking at finding limits of sequences. Limits in the sense that, so the majority of the sequences that we study have a starting point. And so when you think about the limit of a sequence, you're thinking about as you go out to like the infinite term, is the sequence approaching something? And in the previous video, we worked example problems where we found limits of sequences where we were given the formula for the nth term, so a function of n. But there's also the case where you could have a recursive formula. So how do you analyze a sequence from a limit standpoint if you have a recursive formula? So, okay, show that the sequence defined by this recursive formula is increasing and a sub n is less than 3 for all n. Deduce that the sequence is convergent and find its limit. Okay, so what we're going to do is we're going to use the monotonic sequence theorem to show that this sequence is convergent. And so the monotonic sequence theorem says that every bounded monotonic sequence is convergent. So remember, bounded means it has to be bounded both above and below, and monotonic means it's either increasing or decreasing. So we're first going to show that using the monotonic sequence theorem, we're going to show that the sequence is convergent, and then we're going to find the limit. And we're going to do this. We're going to show that it's convergent with the monotonic sequence theorem using mathematical induction. So, but first, let's write out some of the first 5 or 6 terms of the sequence, just so we can get a feel for the sequence. So, all right, it starts off at 1. A sub 1 is equal to 1. A sub 2 is equal to, so you can see a sub 2 is going to be when n is equal to 1. So we have 3 minus 1 over a sub 1, which is 3 minus 1 over 1, so 2. Okay, a sub 3 is, so that means when n is equal to 3, so you have 3 minus 1 over a sub 2. 3 minus 1/2 is 2.5. A sub 4 is, so 3 minus 1 over 2.5. So 3 minus 1 over 2.5 is 2.6. A sub 5 is going to be 3 minus 1 over, so 3 minus 1 over the answer, 2.6154. A sub 6, so 3 minus, so 3 minus 1 over the previous answer, 2.6177. Let's go one more. A sub 7 is equal to 2.6180. Okay, so it does look like this is increasing, right? Every single term that we wrote out is greater than the previous term. And so if it is increasing, then it's definitely bounded below at 1. And then it also looks like it could be bounded above, perhaps at 3, or it could be definitely less than 3 and bounded. That means it would be bounded above at either 3 or some number less than 3. It looks like it would never get to 3. So, okay, but we need to prove this. We're going to do this using mathematical induction. So, okay, we're first going to show that, let's prove that it's an increasing sequence. So Okay, we're trying to show that a sub n plus 1 is greater than a sub n. Okay, so with induction, we first show that this is true for a sub 1. So when n is equal to 1, that means a sub 2 would be greater than a sub 1. So a sub 2 is 2, a sub 1 is 1, and 2 is greater than 1. Okay. So now we're going to assume that we're going to go to the change into k for the induction process. We assume that this is true, that a sub k plus 1 is greater than a sub k. We're assuming that this is true. Now we're going to use algebraic manipulation to show that this is true for like the next term, which would be like a sub k plus 2 is greater than a sub k plus 1. And then if we show that, then by the mathematical induction, we've proven that this is true, or this is true for all n. Okay, so what we're going to do, we're going to use the main formula. We're going to try and put this into a form like this. All right. First, let's divide both sides by a sub k plus 1. Okay, now let's divide both sides by a sub k. Okay, now let's add 3 to both sides. Okay, now let's subtract both sides by 1 over a sub k and 1 over a sub k plus 1. Okay, so now we can match it up with this recursive formula definition. So this is a sub k plus 1. That's exactly this formula. So okay, and we can see that this is going to be a sub k plus 2. And there we go. We assumed that this was true, kind of our original thing we're trying to prove. We changed to k and assumed that was true, and then we showed that it's true for the next term as well. A sub k plus 2 is greater than a sub k plus 1. So we've proven with induction that this is an increasing sequence. Okay. Next, we want to show that, well, okay, let's come back. Since we know that it's increasing and it starts at 1, then that means it's bounded below at 1 for sure. So now we just want to show that it's also bounded above. And so with that, then that means since it's bounded below and above, that means it's bounded in general. And then since it's monotonic, increasing, then that means it's convergent according to the monotonic sequence theorem. So we're going to show that it's bounded above, and we're going to show that it's bounded. It's definitely less than 3 for all n. Now, does that mean it's bounded above at 3? We'll see. But if it's less than 3 for all n, then it's definitely bounded above by something, either 3 or something less than 3. Okay, we're trying to show that for all n, a sub n is less than 3. Okay, so using induction, we need to show for the first term that this is true. So a sub 1 is equal to 1, and 1 is less than 3. Okay. Now we're going to go to the k, change into k for the proof, for the induction. We're going to assume that this is true. We are assuming that this is true. Now we want to use algebraic manipulation to show that this is true for a sub k plus 1. Okay. So we're going to start by dividing both sides by a sub k. Now we're going to divide both sides by 3. Okay, now let's just go ahead and flip this because I want the a sub k for some reason. I just feel more comfortable with the a sub k term on the left side. Okay, now we're going to add 3 to both sides. Okay, now we want to subtract both sides by a sub k. Okay, now we want to subtract both sides by 1/3. Okay, so let's so let's flip it again. 3 minus 1 over a sub k is less than, so 3 minus 1/3 is 2 2/3. Okay, 3 minus 1 over a sub k is a sub k plus 1 is less than 2 2/3, which is less than 3. So there we go. We've shown that a sub k plus 1 is less than 3. And it looks like it could be bounded above by 2 2/3, potentially. A sub n is always less than 2 2/3, but maybe it's less than that. We have to prove what it's actually bounded above by. But we've shown that no matter what, we've shown that it's bounded and it's monotonic. So the sequence is convergent according to the monotonic sequence theorem. So now let's go ahead and find what the limit is. Okay, we're going to say that the limit as n approaches infinity of a sub n plus 1 is equal to the limit as n approaches infinity of what is a sub n plus 1? It's 3 minus 1 over a sub n. Okay, so now we can use the limit laws. We could for sequences, but they're the same for sequences and functions. We could apply the limit here and here. Okay, so we have the limit as n approaches infinity of 3 is just 3. Okay, then the limit as n approaches infinity of 1 over a sub n, we can bring the limit to the numerator and denominator. So the limit as n approaches infinity of 1 is just 1. Okay, and then so we've got 1 over the limit as n approaches infinity of a sub n. That's what we're looking for. Okay, and we know that it's convergent. So we can just replace this with an L. Right? This is like signifying that there's an actual number here. Since we know it's convergent, we can just replace this with an L. Now, okay, what is this equal to? It's equal to this. But the limit as n approaches infinity of a sub n plus 1 is the exact same thing as the limit as n approaches infinity of a sub n. It's just L, right? Do you agree with that? A sub n plus 1 and a sub n is the same sequence. It's just two ways of representing the exact same sequence. Okay, so we need to solve the equation, this equation. All right, let's multiply the entire equation by L. So we've got 3L minus 1 is equal to L squared. So L squared minus 3L plus 1 is equal to 0. Quadratic equation. Let's use the quadratic formula. L is equal to minus B plus or minus B squared minus 4 times A times C over 2 times A. Okay, so L is 3 plus or minus 9 minus 4 is the square root of 5 over 2. So we've got two possible answers here. We've got 3 plus the square root of 5 divided by 2 and 3 minus the square root of 5 divided by 2. Okay, so it can't be this, right? Because the sequence we've proven is bounded below by 1. But but this makes sense. It's not 2 2/3. 2 2/3 would be right, but so this is the limit, and this is what it's bounded above by. Remember, with a limit, the function never gets to the value of the limit. That's what it's approaching. So this is the limit, and this is what it's bounded above. The sequence is bounded above by. So the limit is 3 plus root 5 divided by 2. Okay, now we're going to do another problem, and it's similar to the previous problem. The numbers are similar, but there's some subtle differences. So, okay, same type of problem. Here's the recursive formula. We want to show that it's bounded between 0 and 2, and it's decreasing. And that will show that it's convergent. And then what the convergence allows us to do is set up that formula with the L in it. So, okay, let's first write out the first few terms. So a sub 1 is equal to 2. A sub 2 is 3 minus a sub 1. So 3 minus 2 is 1 over 1 is 1. A sub 3 is 3 minus 1 is 2. 1 over 2, so 0.5. A sub 4 is going to be 3 minus 0.5. 1 over 2.5 is 0.4. A sub 5 is 1 over 3 minus the previous answer. 0.3846. A sub 6 is 1 over 3 minus the previous answer. 0.3824. A sub 7 is 1 over 3 minus 0.3820. All right, so it does look like it's decreasing. Every term that we wrote out is less than the previous term. And if it's decreasing, it would be bounded above at 2. And then it looks like it could go on forever and never get to 0. But it looks like it's gonna it won't it doesn't look like this 0 is the lower limit. It looks like there's another lower limit, but definitely greater than 0. But okay, we have to prove this. Okay, let's first show that it's decreasing. So we're trying to say that a sub n plus 1 is less than a sub n for all n. We start with it for induction. We start by showing that this is the case for the first term. That means a sub 2 would be less than a sub 1. A sub 2 is 1. A sub 1 is 2. So yes, this is true for the first term. So now we go to k, and we're assuming that this is true. So now let's show that with the algebraic manipulation, let's show that this is true for like the second term, which would be like a sub k plus 2 is less than a sub k plus 1. Okay. So let's kind of following the format here, trying to get into use this formula, get into the form like this. Let's first, okay, so we want to add 3 to both sides. Okay, now we want to subtract both sides by a sub k plus 1 and by a sub k. Okay, now we want to divide both sides by 3 minus a sub k. Now we want to divide both sides by 3 minus a sub k plus 1. Okay, we've got 1 over 3 minus a sub k is a sub k plus 1. 1 over 3 minus a sub k plus 1 is a sub k plus 2. And there we go. A sub k plus 2 is less than a sub k plus 1. So we've proven that this is decreasing. And so since it's decreasing, we know that it's bounded above by 2 for sure, because it starts at 2. But is it bounded below? And we're going to say that, assume that it's bounded below by at least 0. So, all right, so we're trying to prove that a sub n is for all n or is greater than 0. A sub n is greater than 0. Okay. So first, is this true for the first term? A sub 1 is 2, which is greater than 0. So yes, it's true for the first term. All right. We're going to assume that this is true. Okay. So now let's add 3 to both sides. Now let's subtract both sides by a sub k. All right, now let's divide both sides by 3 minus a sub k. Now let's divide both sides by 3. Okay, and now 1 over 3 minus a sub k is a sub k plus 1. Okay, so this for all k, this is greater than 1/3, which is greater than 0. So there we go. We've proven a sub n is greater than 0. So by the monotonic sequence theorem, this sequence is convergent. So with that information, let's find the limit. So the limit as n approaches infinity of a sub n plus 1, which is the same as the limit as n approaches infinity of a sub n, which is going to be a number L for sure, is equal to the limit as n approaches infinity of 3 minus a sub n. Okay, so now with the limit laws for sequences, which again is the same as the limit laws for functions, we can write this way. We could say 3 minus right. Limits are really versatile this way. They're easy to work with. You can apply that. You can kind of like just like focus on the area with the variable like that. Okay, but again, the limit as n approaches infinity of a sub n, that's what we're looking for. That's just a number L. We know it's convergent and it's a number L. So, and that's the same thing as the a sub n plus 1 and a sub n are the same sequence. Just one's a different formula. They have the same limit. So there we go. We need to solve for L here. So let's multiply this entire equation by 3 minus L. We get 1 is equal to L times 3 minus L. 1 is equal to 3L minus L squared. So L squared minus 3L plus 1 is equal to 0. Okay, this is the same equation that we had before. So it's 3 plus or minus root 5 divided by 2. L is equal to 3 plus or minus root 5 divided by 2. So we had 3 plus root 5 divided by 2 and 3 minus root 5 divided by 2. Okay, so we're bounded above by 2, so it can't be this. And we're bounded below by 0. At least we haven't proven what we're bounded below by, but we're definitely bounded below by at least 0, or at most something like that. So, but this is what the limit's going to be: 3 minus root 5 divided by 2. And also, this is what it's bounded below by. Okay, so there we go.